Good morning, good afternoon, and good evening to everyone on site or online. We are from the National Yangming Jiaotong University, the Department of Electrophysics. This is an original work done by Yazi Wang. She was a master student in our lab. I am her supervisor, J.W. Zhong. Today I'm presenting this work for her. The topic is milky translucent haze of a large-scale topological defect array in nematic liquid crystal, which looks like this. This is the milky translucent haze. If we take a closer look, actually it's quite complicated. We can see diffraction, we see lens imaging, and we see the scattering. So Yazi got really interested in these beautiful effects. She spent 2 years on research about it. And actually this is a beautiful side effect of our main research. So in our research group, we mainly focus on creating topological defect arrays in liquid crystal. The radial and the hyperbolic defects are created by patterned electrodes and arranged into a large array. And by chance, Yazi noticed the beautiful visual effect like this. So she got very interested, and she spends 2 years to understand the optical properties of the defects, and then she tried to optimize the milky haze effect for smart windows. This is the generation of topological defect, and the formation of defect follows topological rules. The number and types of defects depends on the Euler number of the closed boundary. In a homeotropic sphere with Euler number of 2, there is 1 plus 1 defect at the center. And in the homeotropic toroid with Euler number of 0, the total topological charge should be 0, and we have different choices. It can be no defect, it can be 1 plus 1 defect, 1 minus 1 defect in a pair, or we can have pairs of plus and minus defects inside the toroid. Okay, so then this is our liquid crystal cell. The liquid crystal is sandwiched in glasses coated with transparent electrode. The bottom electrode is patterned. When the electric field is applied, the electrode operated the liquid crystal. The configuration can be like this or like this, and we can have a point defect at the center, or we can just have an escape, but we have surface defects on the substrates. It depends how we treat the surface. This is the case with anti-parallel alignment, and this is the case with parallel alignment. Yeah, okay. And here are the pattern electrodes. We have a lot of choices. We have pixel electrodes like circular pad, annulus, and we have square array, we have hexagonal array, and we have sizes from 200 micrometers to 50 micrometers. So this is quite a large range. Okay, when the defect array is created, then we put it under a polarized optical microscope and we just observe it. The birefringence colors and the brightness are related to the polar angle and the azimuthal angle of the liquid crystal directors. We can just use those information to derive the director field. And again, we can identify the topological defects with the brushes right here. Okay, so this is our observation. And here we would like to discuss the 3 important optical properties here: lens imaging, scattering, and diffraction. First, we start from lens imaging. But honestly, this is very hard to see it from the picture right here. I have to describe it. I have to just try to describe what we see here. So when we hold the tessel in our hand, and if we just see through the tessel like we are looking through a little window, we will see multiple images magnified, overlapped on the other side of the tessel. And it feels like we are just looking through an array of convex lenses. But unfortunately, we cannot see it on the picture right here because those magnified images are virtual image. So we should stand in front of the tessel and looking at it, just look at it by ourselves. Yeah, okay. And the other thing to notice is that when the object is very close to the tessels, then the lens effect and the colorful dispersion just disappear. Okay, so this is about lens imaging. And then the second thing is scatter. Yep. So this is the position of a defect under a optical microscope. When the liquid crystals are at the core of the defect, they are just taking a lot of pressure, so they will melt and they turn from a nematic state into an isotropic state. Therefore, at the core of the defect, the birefringence, the delta n, is 0, and the refractive index at the core and the refractive index outside the core, they are different. There is a dramatic change on the boundary, and the delta n is having a dramatic change on the boundary too. So when light is passing through the defect arrays and they experience that dramatic change on the interfaces, and that's just leading to strong scatter of light. And when we have a lot of defects, then we have multiple scattering. So that is the main reason for the haze. And finally, this is diffraction. So again, due to the 0 delta n at the core of the defect core is somehow just like an aperture. So when we let the light through the defect arrays, it's just showing a diffraction pattern like a two-dimensional grating. We can take the distribution of the defects, and it's directly related to the optical path difference. Then we do a two-dimensional Fourier transform. The result is a spectrum of special frequency of the defect distribution. And the special spectra is just the diffraction pattern, so we can do the comparison of it. We check the patterns by the equations right here, and here you can see the correspondence of the defect distribution and the diffraction pattern right here. They agree with each other. Okay, so this is showing how the defect array changes with respect to the applied voltage. So when the applied voltage is 3 volts, the +1 defect at the center of the electrode just appear, and this is the special spectra of the defects, and we can compare it to the diffraction pattern. When the applied voltage is 6 volts, and we have hyperbolic defects right here, and this is the special spectra of the +1 and the hyperbolic defects, and this is a superposition for it. The experimental results agree with the estimation, and we just mark that the change is that the diagonal component right here is getting brighter. And when the applied voltage is 15 volts, and additional defects on the corners of the pixels just appear, and we have 3 special spectra for 3 types of defect, and we have the superposition and compare it to the experimental results, but it's showing an unexpected effect right here. So the defects on the x direction and on the y direction, they are getting brighter, but the defects on the diagonal directions, they are getting darker, they are fading away. This is unexpected. So we just suppose that maybe the light through 3 kinds of defects, they have different phases, and that phase difference somehow can lead to destructive or constructive interference. So we see a results like this. some more investigation is required to give an exact answer. Okay, so finally we come to the most important question: how to get the best Milky haze. We take the test cells to a professional lab to measure the haze, and generally the haze is defined as how many percentage of the light is away from the original beam. However, that measurement shows that the Milky translucent test cells give a large haze, but the test cell like this with strong diffraction, strong dispersion, and strong glittering effect, they are giving a high haze too. And this one is the comfortable one, and this one doesn't look really, this is not very easy to look at it, it's very sharp. So now we just try to suggest that maybe we should add another analysis to it. We can just do the Fourier transform analysis, do the special spectral analysis. If the defects are regularly distributed, we see very sharp diffraction patterns right here, then usually it gives strong multiple images and dispersion. And when the defects are distributed in a very messy way, and if we do the special frequency analysis, we will see a lot of special spectrum right here. And this is the feature when we have the comfortable milky transparent liquid crystal cell, and the visual effect is more like the translucent material. And finally, here is the combination of different kind of choices. So we have combinations of pixel shape, and we have array structures, square and hexagonal, and we have pixel sizes. And just look at the results, we can just see it very obviously that this is the best case. So when we have, and actually this is a hexagonal array with donut pixels, and when the pixel size is 20 micrometers, and it's giving us the massest defect distribution, and it gives us a continuous special spectra, and you can see the Milky haze right here. So here are the key parameters. We have pixel pattern, array arrangement, and pixel size, and we can play around with it. Okay, so finally we come to the conclusions. We just analyze the optical properties of topological defects, and we find the key parameters to create the best Milky haze. And thank you very much for your attention. I hope you enjoyed the talk. Thank you.